It does not explode slowly. It releases everything at once. Energy beyond scale. Radiation beyond shielding. A single burst can erase a system, and nothing nearby can survive it. Space looks empty, silent, still, endless. But signals repeat, stars collapse, planets burn. Some things out there should not exist. This is Space Horrors, the universe that should not exist. A star looks stable because it lasts longer than civilization. It rises, it sets, it burns for millions of years. So we call it permanent. But permanence is not safety. A star is a balance between two forces, gravity pulling inward, radiation pushing outward. For most of its life, that balance holds. Then the fuel changes, the core changes, the pressure changes, and the star stops behaving like a light source. It becomes a stored weapon of physics. Not because it chooses anything, not because it targets anything, because energy has to move. And when a massive star fails, that energy does not stay local. It crosses orbits, it reaches atmospheres, it changes chemistry, it turns distance into the only shield. This is the first rule of system-scale extinction. The planet does not have to be struck. It only has to be close enough. The most dangerous stars are not always the ones that look the brightest from Earth. They are the ones burning through themselves too fast. Hypergiants are among the extreme examples. They are huge, unstable, and short-lived on cosmic timescales. Their outer layers can be pushed outward by radiation. Their surfaces can shed material. Their winds can carry away mass faster than ordinary stars ever could. Around them, space does not stay clean. It fills with gas, dust, old eruptions, shells of material thrown away before the final collapse. This matters because the star is preparing its surroundings. It is loading the system with material that can be struck later. It is shaping the blast before the blast exists. A planet orbiting nearby would not see a single warning sign. It would see many. Brighter radiation, changing winds, more particles, a star that no longer behaves evenly. Then the system enters its dangerous phase. Not at the moment of explosion, before it. The death of a massive star begins while the star is still shining. Inside the star, the real disaster begins where no one can see it. The core runs out of the support it needs. Gravity gains control, and the center falls inward. This collapse is not slow. It is sudden, extreme, compressed into a moment where the star can no longer hold itself up. The outer layers are still there. The planets are still in orbit. The system may look unchanged, but inside the star, the structure has already failed. That failure sends energy outward. A shock moves through the star. Radiation escapes. Particles accelerate. Material is thrown into space. For a nearby world, this is not just bright light. It is a change in the environment around the whole planet. The sky receives high-energy radiation. The upper atmosphere is forced into chemical reactions. The magnetic environment is disturbed. The protective layers begin to weaken. The star does not have to touch the planet. The collapse reaches it first. The most dangerous release is not always the widest one. Sometimes it is the narrowest. A gamma-ray burst does not behave like a campfire. It does not warm everything gently in every direction. In many cases, it is a jet, focused, fast, violent. A beam of high-energy radiation moving through space. If that beam is pointed away from a planet, the planet may never know it happened. The system may survive because geometry protected it. But if the beam is aimed toward a world close enough to receive it, distance stops being abstract. It becomes the difference between survival and collapse. Gamma rays do not need clouds to part. They do not need oceans to boil. They attack the upper atmosphere first. They ionize molecules. They trigger chemical chains. They can weaken the layer that normally blocks dangerous ultraviolet radiation from the parent star. The burst itself may be brief. Seconds, minutes, then it is gone. But the damage it starts can last far longer than the flash. That is what makes a beam more frightening than an explosion. It can miss almost everything and still destroy the thing in its path. A planet survives space because it carries a shield, not a wall, an atmosphere. Layer by layer, it absorbs radiation, deflects particles, slows energy before it reaches the surface. Life depends on that delay, on that filtering, on that chemistry staying stable. A nearby gamma-ray burst attacks that stability. The first damage happens high above the ground. Molecules are broken apart. New compounds form. The ozone layer can be reduced. Ultraviolet radiation can reach deeper than normal. The event in space may already be over. But the planet is still changing. The surface receives more radiation. Food chains are stressed. Climate can shift. The chemistry of rain and air can be altered. This is not the drama of a planet exploding. It is quieter than that, and more realistic. The world remains in orbit. The oceans may still move, clouds may still form, but the shield is damaged. And once the shield is damaged, the surface is no longer the same place. A system can be killed without being broken apart. The star does not always stop being dangerous after it dies. Sometimes what remains is worse. A magnetar is a kind of neutron star, small compared with ordinary stars, dense beyond normal matter, and surrounded by a magnetic field so extreme it changes how the object behaves. It is not large, but size is not the point. Energy density is. When a magnetar releases a giant flare, the flash can be detected across enormous distances. One famous event from SGR 1806-20 was powerful enough to disturb Earth's ionosphere, even though it came from far across the galaxy. That does not mean Earth was in direct danger from that event. Distance protected us. But move a planet much closer, place it inside the wrong neighborhood, then the same category of event becomes something else. A burst of X-rays and gamma rays, a shock to the upper atmosphere, a sudden change in the radiation environment of an entire world. The disturbing part is not that a dead star can flash. It is that the dead star can still reach out. When people imagine cosmic destruction, they imagine impact, a collision, a fireball, a planet torn open. But the universe has quieter ways to end habitability. A planet can keep its shape, keep its orbit, keep its mountains, and still lose the conditions that made it livable. Radiation can strip electrons from atoms. Particles can erode the edge of an atmosphere. A star can lose mass and change the gravitational balance of nearby orbits. A blast wave can compress or sweep through surrounding gas and dust. None of this requires a direct hit. It requires exposure. That is why a system-wide killer is different from a local disaster. It does not choose a crater. It changes the rules around every planet close enough to feel it. The inner worlds receive the harshest radiation. Outer worlds may lose fragile atmospheres. Moons may be sterilized at the surface. Dust and gas may be reshaped around every orbit. The system survives as a structure, but as a home, it may be gone. This is where the science matters most. Not every violent star is a threat. Not every burst is aimed at a planet. Not every system sits close enough to be destroyed. Space is vast, and vastness is protection. A gamma-ray burst can be one of the most powerful events in the known universe, and still be harmless if it is too far away. A magnetar flare can disturb detectors from across the galaxy, and still leave a world safe because distance weakened the energy. The danger comes when the conditions align. A powerful source, a closed system, a directed burst, a weak or vulnerable atmosphere, a planet in the wrong place at the wrong time. That combination is rare, but rare does not mean impossible. The galaxy does not need these events to happen often. It only needs them to happen once, close enough, and pointed the wrong way. For planets, survival is not only chemistry, it is location. After the burst, space becomes quiet again. The flash is gone. The star field returns. The planets continue moving. From far away, the system may still look intact. A telescope may still see orbits, clouds, reflected light, a world turning slowly in the dark. But habitability is not something a telescope can always see immediately. It lives in thin layers, in chemistry, in atmosphere, in shielding, in the narrow conditions between too much energy and not enough protection. A hypergiant can prepare the system with winds and mass loss. A collapsing star can send the shock. A gamma-ray burst can deliver the beam. A magnetar can prove that even a dead star can still disturb a world from impossible distance. Different mechanisms, same warning. A star is not only a source of light. Under the wrong conditions, it can become the thing that removes every safe place around it. The universe is filled with invisible warfare. Radiation crosses space constantly. Particles move through matter unseen, and over time, exposure changes everything alive. The universe does not need monsters. It has gravity, radiation, pressure, vacuum, and somewhere beyond what we can see, the next anomaly is already moving. This is space horrors, the universe that should not exist.